atom is the smallest unit of matter that still retains the chemical properties of a particular element. Atoms, in turn, are composed of even smaller parts called protons, neutrons, and electrons. The specific arrangement of these subatomic particles gives rise to the chemical and physical properties of the element. Chemical properties refer to the properties that determine the chemical nature of matter. Examples include combustibility and the ability of a substance to react with other substances. For example, molecular hydrogen is combustible, carbon dioxide is not. Physical properties do not involve chemical changes. Examples include color, shininess, and freezing point. For example, water is colorless and has a freezing point of 0 degrees centigrade. All atoms consist of an atomic nucleus and an outer region containing electrons. The atomic nucleus is the core of an atom, and it contains protons and neutrons. A proton is a subatomic particle that has a positive charge. A neutron is a subatomic particle that has no charge, and electrons are subatomic particles that are negatively charged. Electrons move in orbitals or rings around the atomic nucleus. Each subatomic particle has an electric charge and a defined amount of mass, measured in atomic mass units, AMU, or daltons. The mass of a single proton or a single neutron is about 1 dalton. Electrons have a mass that is much smaller than the mass of a proton and a neutron, so electrons contribute little to the overall atomic mass of an atom. However, because an electron is negatively charged, it does contribute to the atom's total charge. All atoms of a particular element have the same number of protons in the nuclei. This number of protons, which is unique to that element, is called the atomic number. For example, helium's atomic number is 2, which tells us there are 2 protons in the nucleus of a helium atom. An atom's mass number is the value that is equal to the number of protons and neutrons in the nucleus of an atom. As mentioned earlier, electrons have a negligible mass, and so they don't contribute to the overall mass of an atom. Again, all atoms of a particular element have the same number of protons in the nuclei. However, the number of neutrons can differ between atoms of the same element. These different atomic forms are called isotopes. Isotopes have the same atomic number, but they have different mass numbers. For example, carbon-12 and carbon-14 are 2 isotopes of the element carbon. Both isotopes have 6 protons, but carbon-12 has 6 neutrons, while carbon-14 has 8 neutrons, resulting in different mass numbers. We spent a lot of time talking about protons and neutrons. Let's focus our attention now on electrons. It turns out that atoms have the ability to gain or lose electrons, and when this happens, an ion is formed. Atoms which neither gain nor lose electrons are neutral. For example, a carbon atom has 6 negatively charged electrons and 6 positively charged protons. These charges cancel each other out, leaving you with a neutral atom. When atoms gain extra electrons, they become negatively charged ions, or anions. For example, a fluorine atom can gain an extra electron to fill its outer shell, resulting in an atom with 9 protons and 10 electrons, which leaves you with an overall charge of -1. When atoms lose electrons, they become positively charged ions, or cations. For example, a sodium atom can lose an electron from its outer shell, resulting in an atom with 11 protons and 10 electrons, so an overall charge of +1. Several models have been proposed to describe how electrons behave. One of the earliest models, the Bohr model, was developed by Danish physicist Niels Bohr in 1913. In his model, Bohr shows electron shells surrounding the nucleus. Electron shells are denoted with the number and the symbol N. Electrons fill each shell in a specific order. Electrons found in the shell closest to the nucleus are at a lower energy state than electrons in the outermost shell, and each electron shell can only hold a certain amount of electrons. The inner shell closest to the nucleus can only hold a maximum of 2 electrons. Subsequent shells can hold more. This is known as the octet rule. Atoms typically completely fill their outermost electron shell in order to achieve maximum stability. While the Bohr model is useful for understanding the relationship between number of electrons and chemical reactivity through the octet rule, it does not accurately represent the distribution of electrons in an atom. It turns out that scientists are unable to determine the absolute location of an electron in space and time, but they do know that electrons move within atomic orbitals, a region of space with a specific shape which surrounds the atomic nucleus. With the help of mathematical equations, scientists are able to use the orbitals to predict where an electron might be at any given time. An electron shell consists of 1 or more subshells designated by the letters S, P, D, and F. The letter of the subshell indicates the shape of the orbital, and each orbital holds a maximum of 2 electrons. For example, orbitals in S subshells are spherical, while orbitals in P subshells are shaped like dumbbells.